Hi everybody, welcome to this video in which we shall learn about basic data types in statistics. Specifically, we shall discuss discrete data and how to visualize trends in data. But first, quickly discuss what is a statistic. Well, it is a number computed from a given data set. It describes some property of a given data set. For example, what is the average value of the data? It is important to remember that statistics mean only something in the context of a given data set. For example, saying mean weight of 22 kg is meaningless without stating whether we are talking about weight of infants or grown-up adults. So given that there must be a data set to compute a statistic, question is what kind of data we may be encountering. Well, the data can be qualitative. This often reflects an opinion. For example, that's a nice coat. The word nice represents a quality. In contrast, quantitative data measures quantities. For example, the coat costs 300 pounds. Quantitative data in turn has two main types. It can be discrete and it can be continuous. In this video, we shall discuss the discrete data in some detail. Discrete data takes only exact values. For example, the number of students in a class, the number of cars on the street, or the numbers of subscribers on a YouTube channel. No matter how many subscribers are there, they're still discrete. There are no fractional values. For example, even if the video says there are 1.16k subscribers, it actually means 1,160 subscribers. Note the data in its raw form, or in other words, as you received, may be unordered. For example, as on your screen. So there are a bunch of values, they are not necessarily in order. And why do they have to be in order? Do they even have to be in order? That will become clear as we go discussing some other topics downstream. Now suppose we have some discrete data, for example, your test scores. What can we do with it? Well, one thing we can do is we can count how frequent variance scores are. Or in other words, how many students got which score. So we notice 1 appears only once. So we note it down in this so-called frequency table. Similarly, we see 2 appears twice in the data set. So we record it as is. And this way we keep recording the counts or frequencies of each mark. Now we can also count how many students score up to a certain mark. For example, how many score up to 3 or below. This is called cumulative frequency. So to compute the cumulative frequency, we start with the lowest mark, which is 1, and we see only 1 student scores up to one mark. Now to compute how many students scored up to the next mark, which is 2, we add the frequencies of both 1 and 2. In other words, we accumulate frequencies as we go down the table. Hence the name cumulative frequency. So the frequencies of the mark 1 is just 1, whereas the frequency of mark 2 is 2. So 2 plus 1 gives you 3, hence 3 in the second row. Similarly, we keep accumulating frequencies as we go down, and thus the total number keeps going up and up, as you might have noticed already in the third column. Note one hint that you computed the cumulative frequency correctly is that the last or the bottom number in the cumulative frequency column must equal the total number of data points. So in this case, there are 10 data points, as you can see, you can count the numbers at the top of the slide, and so is the last cumulative frequency. Now let's see how we can visualize frequencies. All the frequencies put together in any form is called a frequency distribution. For example, here we drew a table of frequencies. So the table represents a frequency distribution. To draw this, we can use what we call a bar chart, where on the x-axis, we write down each unique number from our original data set. Each number is spaced out only to make it easy to see them. Otherwise, the distance doesn't really mean anything. On the y-axis, we plot frequency of each data point. And to plot frequency, we must choose a suitable scale. So once we have the scale on the y-axis, we draw the bars of appropriate lengths to show the frequencies. For instance, the first bar goes up to only 1, which matches its frequency. Second bar goes up to 2, which also matches, and so on. Notice there is no scale on the x-axis. There's only a scale marked out on the y-axis. This is because the distance between each data point on the x-axis is immaterial. We simply want to separate them out so each bar visually looks different or distinct. There is no other purpose of this distance between bars, and hence we don't need a scale on the x-axis while drawing bar charts. This is important because bar charts are also used to show categorical data, where each point is a rating or opinion. For example, let's replace these marks with ratings, such as this. Then the labels on the x-axis will change, but the rest of the bar chart doesn't because frequencies are still the same. And now I hope you can see that the distance becomes a meaningless concept between ratings such as great or good. If not, you can pause the video and convince yourself. I mean, how would you create a distance between great and good? And even if you do manage to define a distance, would others agree with that or not? A pie chart can also visualize frequency distributions of discrete data. In this case, all the frequencies are converted into percentage shares of the total sum of frequencies. And then each percentage is given a share of the pie. For example, or in this case, we have not exactly drawn a pie, we have drawn a donut shape, but I mean, still effectively the same. So, the greater the percentage, the greater is the share of the pie. So, yeah. Another way of showing data in terms of its percentages is tree map graph, as it is called in Microsoft Excel. Again, you can see that the biggest rectangle goes to the largest frequency, which in this case is for the data element week. It occupies 50% of the rectangle because in the frequency table, you can verify it is indeed the case. Unlike the pie chart, there seems to be an order from the biggest area to the smallest area. However, a difficulty of visualization arises due to the shapes of the rectangles. For example, if you focus at the rectangle for great and the rectangle for OK, the frequencies behind both these rectangles are identical, yet the two rectangles look different. And so you have to guess whether their areas are actually same or different. So each method has its own pros and cons. But with this, we conclude the discussion of categorical data, and we will see you in the next one about continuous data.